You've seen them your whole life. Those gray, jagged stones scattered between railway tracks, stretching as far as the eye can see. They're there at every train crossing, every station platform, every stretch of track cutting through the countryside. Most of us glance right past them without a second thought. But have you ever stopped to wonder why they're there at all? Why not just lay the tracks directly on the ground or pour a concrete base like we do for roads? And why stones specifically, not gravel or sand or something smoother? What would actually happen if someone built a railway without them? The answer turns out to be far more clever than you'd expect, and it reveals something fascinating about how we solve problems that seem simple on the surface but are surprisingly complex underneath. Let's talk about what's really happening here. When a fully loaded freight train rolls down the track, it can weigh over 10,000 tons. All of that weight is concentrated on two thin strips of steel, pressing down with immense force every single time the wheels pass over. This happens dozens, sometimes hundreds of times a day on busy lines. And it happens in blazing summer heat, in freezing rain, through winter frost that makes the ground heave and shift. The actual challenge isn't just keeping the rails from moving. It's preventing the entire track system from slowly destroying itself. The ground wants to compact and settle unevenly. Water wants to collect and weaken the foundation. The immense repetitive force wants to drive the rails deeper into the earth or knock them out of alignment. And remember, a train moving at 60 miles per hour needs the track to be aligned within fractions of an inch, where the consequences can be catastrophic. So the solution? Those unremarkable stones you've been ignoring. They're called ballast, and they're performing a job that seems almost impossible for such a simple material. Here's what's actually going on beneath a train. The ballast isn't just sitting there. It's a carefully designed system of angular crushed rock, usually granite or basalt, each piece between 1 and 3 inches across. When the train's weight pushes down on the rails, that force transfers through the wooden or concrete ties and into millions of individual stones below. Each stone touches several others at sharp angles, and together they create a network of interlocking contact points. When pressure is applied, the stones shift microscopically, spreading the load outward and downward across a much larger area. Then, when the train passes, they lock back into position. Think of it like this. Imagine trying to push your finger into a box of rice versus pushing it into a bowl of water. The water just moves aside and offers no resistance. But the rice grains, even though they can shift and flow, resist your finger because they're pressing against each other from every direction. Ballast works the same way. Each stone is rigid and hard, but the system as a whole can absorb force, distribute it, and spring back into shape. Now, if you asked most people why the stones are there, they'd probably say it's for drainage. And that's not wrong exactly. The gaps between the stones do allow rainwater to flow away instead of pooling around the tracks, which prevents rust, rot, and erosion. But if drainage were the only purpose, you could use much cheaper materials: coarse sand, graded gravel. The real reason ballast has to be angular stones of a specific size is because it needs to do something far more difficult than just letting water through. It has to be strong enough to carry enormous weight without crushing, flexible enough to absorb the shock and vibration of a speeding train, stable enough to keep the rails perfectly aligned over years of use, and yes, porous enough to handle drainage and prevent vegetation from taking root. No other material does all of these things as well, as reliably, or as affordably as crushed stone ballast. So, what does this give us? First, it spreads the train's weight over a much larger area, preventing the track from sinking into the ground. Second, it cushions the impact of each passing wheel, which reduces wear on both the track and the train itself. Third, it drains water away, protecting the wooden ties from rot and preventing ice from heaving the tracks out of alignment in winter. Fourth, it keeps plants from growing through the track bed, which would destabilize everything. Fifth, and this is crucial for maintenance, it can be adjusted. When tracks need to be raised or realigned, workers can tamp more ballast underneath or remove excess stones. You can't do that with a solid concrete slab. And sixth, It's available almost everywhere and costs a fraction of what more engineered solutions would require. Here's where it gets interesting. Ballast wasn't some modern innovation. It was discovered by trial and error in the earliest days of railways, back in the 1820s and 1830s. The first railways in England tried laying tracks directly on the ground or on wooden planks. Within months, the rails would sink, warp, and become dangerous. Engineers experimented with everything from broken bricks to crushed oyster shells. But by the 1840s, crushed stone ballast had proven itself so effective that it became the global standard. Nearly 200 years later, with all our advanced materials and engineering, we're still using essentially the same solution. And it's not just a few old railways. From the high-speed rail networks in Europe and Asia to the freight lines crisscrossing North America, Australia, and Africa, ballast is everywhere. It's one of those rare technologies that works so well in so many conditions that we've never needed to replace it. So, those stones aren't leftovers. They're not an afterthought. They're a precisely chosen material doing an incredibly sophisticated job, hidden in plain sight. The next time you're waiting at a railway crossing, you might see them a little differently. And if this made you curious, maybe just notice the small things around you that you've stopped questioning. Sometimes the most ordinary sights have the most interesting stories.